This lesson is looking at radicals and how to convert between mixed and entire radicals. So radicals are the inverse operation of exponents. So we know that 5 squared is 25, and we look at the radical, the square root of 25 is equal to 5. So for every power, there's a corresponding root or radical. The general format that we use to show them is the nth root of a. The whole symbol is called a radical. The little number inside that root sign is called the index, so in this case it's the n, and a is the radicand. If there's no n shown, it's implied to be a square root. So a couple more examples. Looking at that inverse of exponents, we know that 2 to the 8th is 256, so the 8th root of 256 is equal to 2. 6 to the power 5 is 7,776, so the 5th root of 7,776 is 6. So these examples, the square root of 25, 8th root of 256, and 5th root of 7,776, are all nice rational values because they come out exactly. But there's many that don't come out exactly, that there's not a perfect whole number that is equal to the radical. So with radicals, we can write them as mixed radicals, where we have a whole number portion and we have a radical portion. This is similar to fractions, where we can write them as a mixed number, or we can write them as an improper fraction. So radicals that aren't rational have two possible forms: the mixed radical form and the entire radical form. So the mixed radical form has a rational portion and a radical portion. The entire radical means everything's written as a radical, just like the improper fraction has everything written as a single fraction. So in order to do that, we need to look at one particular property of radicals, which is the multiplication property of radicals. And what that says is we can multiply what's underneath the radical and make it under a single radical, or we can go the other direction. We can take a radical and break it into factors and put each factor under its own radical. So a couple examples here, right? If I have square root of 25 times 9, I can multiply them together and get the square root of 225, which is 15, or I can do them separately. So again, these ones are working out as nice rational values. This will also work when they don't work out rationally. Another example here, cube root of 125 times 8. I can do the multiplication first, which gives me 1,000 under the radical, and the cube root of 1,000 is 10. Or I can do them separately, and I can get cube root of 125 separately is 5, and cube root of 8 is 2, so I'm left with 5 times 2, which is 10. So it doesn't matter which order we do it in with this multiplication property of radicals, we get the same result. So what this has to do with putting radicals in simplest form and in that mixed form is we can split out a factor that's a perfect nth power, right? Whatever our index is. So if we're looking at square roots, we can factor out something that's a perfect square. If we're looking at cube roots, we can factor out something that's a perfect cube, and so on. So when we are simplifying a radical, we're going to take out any perfect factors, and anything that's left over we'll be writing in mixed radical form. So I've got a couple example questions here. So if we have the square root of 675, and we want to look at that for finding some perfect square powers, something that's useful. You don't have to if you can recognize a perfect square pattern without it, but if you have trouble recognizing the perfect squares, a useful thing is making a factor tree. So if we take 675 and we break it up into factors, well, we can see that 5 comes out of 675, which leaves me with 135, and then I can take out 5 again, which leaves me with 27. I can break 27 into 3 and 9, and I can break 9 into 3 and 3. So if I'm looking for perfect squares that come out of this, because it's a square root, that means factors that show up twice. So I'm looking at the leaves of my factor tree, right? Just the things on the very end. So I've got 5 and 5 that are perfect squares. So I can put 5 squared as 2 factors that come out of this. I've also got 3 and 3. So I can write 3 squared as a perfect square factor that comes out of that. And I have one more factor left over. It's not a perfect square, but I can't just leave out any factors, so I put that in its own square root. So I've broken 675 up into the factors in such a way that anything that's a perfect square is under its own square root. So from that, my square root and my square are opposites, so they're going to cancel out. So square root of 5 squared is just 5, because the square root and the square cancel. Likewise, with my square root of 3 squared, I just get 3. My square root of 3, though, no square to cancel out, so it's got to stay inside my square root. So on the outside, I now have 5 times 3, which gives me 15 root 3. I can do the same if I have a higher power, so we're going to do a couple more examples. Next one is with the cube root of 192. So the cube root of 192, again, making a factor tree is going to help me. So we'll do that off to the side. So 192, we can take 2 out of that. 2 goes into 19, 9 times. 2 goes into 12, 6 times. I can take out another 2. 2 goes into 96. 4 times, and into 16, 8 times. Don't have to take out prime factors. I have been up to hell, but it's perfectly okay to take out larger factors, so I can get 4 times 12. 4 is 2 times 2. 12 is 4 times 3. And 4 is 2 times 2. So again, I can look at grouping these, this time not into pairs, because it's a cube root, I'm grouping it into 3s. So 1, 2, 3 2's there. So I've got 2 cubed inside my cube root. Don't forget the number out front. If I have a mixed radical like this one, I've got to keep that value out front. Go back to my next pair of 3, set of 3, so 2, 2, and 2, so I've got another 2 cubed inside my cube root, remember that index. And then my last one, my 3 that's left over, I get cube root of 3. So this, again, cube root is going to cancel 2, so I get 2 times 2 times 2 times the cube root of 3. Which leaves me with 8 cube root of 3. Always a good idea to circle your final answer. And our last one here, cube root, sorry, not cube root, fourth root of 112. So 112, looking for factors that come out of that. Again, 2 is going to come out of that. So 2 and 56. 2 and 29. I feel like I made a mistake. Oh, yes, I see my mistake here. It's not 2 times 29, it's 2 times 28. And that gives me 4 times 7. And 7 doesn't go any further, but 4 does. So again, I can group this, but this time, because it's a fourth root, I'm grouping it into things that show up 4 times. So 1, 2, 3, 4 2's underneath my fourth root. And 7 is left over, so keep that factor. So 2 to the 4 times 7 is equivalent to 112. I haven't lost any of my factors. just putting them in a different form so that I can cancel my 4th root and my 4. I'm left with 2 times the 4th root of 7. So that's taking our radicals and putting them in what's called simplest form, but the simplest form in every one of these cases happens to be a mixed radical form. We can also go the other direction. We can write each mixed radical as an entire radical. And that's where we start out with a mixed radical and we want to put it all under the radical form. So we do that basically the opposite of what we were just doing. So here, I canceled my 4th root and my power 4. Here, I want to put it underneath a root. So I'm going to apply the root, but I'm also going to apply the exponent so I end up with an equivalent expression. So if I have 2 root 3, I can put the 2 underneath the square root if I also square it at the same time, giving me square root of 2 squared. So that is a value I can work out. 2 squared is 4. So I get square root of 4 times the square root of 3. And then I can multiply those together using my multiplication rule of radicals, right? What's underneath the separate radicals can be put into a single radical. So 4 times 3 is going to give me 12. Again, we can do this with higher order radicals. So if I have a cube root or a 4th root, I use the same process, but instead of square rooting it and putting it in a square, I cube root it and I take it to the power 3. So my 5 that's outside the root, I'm going to put inside the root and cube it. And 5 cubed is 125. I multiply that by the remaining factor, the 4, and I get 500. My last one, I've got a 4th root, so if that 3 that's out front, I want to put under the radical and take it to the same power at the same time. So put it under the 4th root and take it to the power 4. So 3 to the power 4 is 3 times 3 times 3 times 3. So 3 times 3 is 9 times 3 is 27 times the last 3 gives us 81. Multiply that by the 5 in my other radical and I get 4th root of 405. In all 3 cases, we end up with just a single number inside our radical form. So if we want an entire radical, that's what we're doing. Exactly the opposite of the other ones where we were looking at simplifying and we ended up with the mixed radicals. I hope that helped.